Chapter 9 Electrolyte Solutions. Section 9.4 Ionic Strength and Mean Activity Coefficients. The ionic strength of an electrolyte solution is denoted by I, and we have an equation for the ionic strength. I is the sum of 1/2 of the molality multiplied by the sum of the cationic term and anionic term. In the cationic term, we have the coefficient of the cations multiplied by the charge of the cation squared. In the anionic term, we have the coefficient for the anions multiplied by the charge of the anion squared. The reason we put a sum here is because in the electrolyte solution, we may have multiple different salts dissolved. For example, we can have both sodium chloride and aluminum sulfate being dissolved in the same solution. Now again, this M sub I is the molality, which means the mole of solute per kilogram of solvent for electrolyte solute I, species I. We're summing it up because again, it's possible to have multiple types of salts dissolved in the same solution. Nu is the stoichiometric coefficient of the ions. Nu is also the subscript number in the ionic formula of the salt, and Z is the charge of the ion. So for example, the Z sub I plus is the charge of the cation in electrolyte I. Alright, now let's look at a couple examples. For a 0.1 mole per kilogram solvent sodium chloride solution, how do we calculate I? We have only one type of salt, so we don't have to do the sum here. It's going to be just 0.1 over 2, so it has to be divided by 2. The coefficient for sodium is 1, the charge is 1. The coefficient for chloride is 1, the charge is 1. Therefore, the ionic strength for this 0.1 mole sodium chloride solution is also 0.1 mole. For a 0.01 mole aluminum sulfate solution, we do similar calculations. I is 0.01 over 2, and now 2 is this number. So when we dissolve just 1 unit of aluminum sulfate, we get actually 2 aluminum cations. Therefore, we have 2 here, multiplied by the charge of this aluminum cation squared, and then plus 3 sulfate times the charge of sulfate squared. So if you look at this 2 terms inside the pair of parentheses, we have 2 times 9 plus 3 times 2, we get 30. And then 30 divided by 2, we get 15. 15 multiplied by 0.01, we get 0.15 mole. So it's really interesting over here. So you can see this concentration is 0.1, this concentration is 0.01. Obviously, sodium chloride has a much larger concentration, 10 times the concentration of aluminum sulfate. But in the end, the ionic strength of this lower concentrated aluminum sulfate has a higher ionic strength than this sodium chloride solution. What if 2 or more electrolytes are dissolved in water, and then we need to sum up all those electrolytes? Or we can say we need to sum up all those ions. Here's another example. Let's have a 1.0 mole KCl and 0.01 mole aluminum sulfate, both dissolved in an aqueous solution. And what's the ionic strength? So now we have to do the sum. Over here, I is from 1 to 2. Species 1 is KCl. Species 2 is aluminum sulfate. We need to sum up everything. For KCl, we have the molality 1.0 over 2 times the coefficient times the charge squared. For potassium, again the coefficient times the charge squared for chloride. And this is the molality of aluminum sulfate, and over 2, and then 2 is this coefficient here, and multiplied by the charge of the aluminum cation squared plus 3, which is the coefficient for sulfate, times its charge squared. So this part is going to be just 1, and this part is going to be 0.15. Together, the ionic strength of this solution of both 1.0 mole KCl and 0.01 mole aluminum sulfate is 1.15 mole per kilogram solvent. Sorry if I forgot to mention, in this example we use 1 kilogram of water, so we're going to assume 1 kilogram of solvent in this aqueous solution. I describes quantitatively the total strength of all ions in the aqueous solution, and that therefore it's called ionic strength. The Debye-Huckel theory states that the mean ionic activity coefficient, so this is gamma plus minus, can be calculated using the following equation when the ionic strength I is low. So this I has to be low before we can use this equation. If I is really high, this equation can still be used but may produce large errors. The natural logarithm of the mean ionic activity coefficient gamma plus minus is equal to negative 1.173 times the absolute value of the positive charge times the negative charge, and then we have the square root of I over m naught. This is to remove the unit in I. Ionic strength by itself is in molo, and then divided by 1 molo we can get rid of the unit. Given the above equation, we can tell that the natural logarithm of the activity coefficient is always negative. So you see the negative sign here, and everything else is positive. So this gamma plus minus is always smaller than 1. This gamma, the mean ionic activity coefficient, is always smaller than 1 because of the attraction between the ions with opposite charges. So if you dissolve an electrolyte in aqueous solution, usually sodium is surrounded by water molecules, and then also by some chloride to stabilize the sodium plus, and chloride is more likely to be surrounded by sodium plus than by other chlorides. So overall there's going to be electrostatic attraction between those ions. Of course there's a repulsion, but when you dissolve electrolytes in an aqueous solution, the attraction between these ions is greater than the repulsion between these ions. And also, of course, there's going to be attraction between the ions and the surrounding water molecules. Now let's look at one numerical example of using this equation. If we have 0.1 mole sodium chloride solution, that means if we have 0.1 mole sodium chloride per kilogram water, alright, we can compute its ionic strength. We have 0.1 over 2, and then over here coefficient times charge squared for sodium, coefficient plus charge squared for chloride, and then we have 0.1 mole as the ionic strength. Now let's compute the logarithm of the mean ionic activity coefficient. We plug in all the numbers, z plus, z minus, they are 1 and negative 1, and then we take the square root of negative 0.1, and overall we get negative 0.371, and then gamma plus minus is e to the power of negative 0.371, it's 0.69. So therefore the mean activity of this 0.1 mole sodium chloride is 0.1 times this mean ionic activity coefficient, which is just 0.069. The mean chemical potential of the cations and anions in such a solution can be expressed this way. Again, this mu is different from mu naught, and over here we have the difference RT times the natural logarithm of the mean activity of these ions. Now let's look at another numerical example problem, 9.4.1. Calculate the ionic strength, the mean activity coefficient, and the mean activity of the ions in this 0.01 mole aluminum sulfate solution. So first, let's look at its ionic strength. We use this formula, but we have only one electrolyte, so don't worry too much about the sum sign. Okay, so we're just summing over only one electrolyte. and the molality of this electrolyte is 0.01/2, and then we have the coefficient multiplied by the charge squared for both aluminum and sulfate, and then we get 0.15 molo. And how do we get the mean activity coefficient? We use this equation proposed by Debye and Herkel. The natural logarithm of the mean activity coefficient is minus 1.173 times 3 times 2. Those are the absolute values of the charges of the cation and anion, and then the square root of 0.15. So over here inside this square root, it's I over m naught. Alright, this is just to get rid of the unit, and then we get negative 2.73, and then gamma plus minus is e to the power of negative 2.73, which is 0.0655. It's pretty small, it's much smaller than 1. Gamma plus minus is the mean activity coefficient. Again, it's impossible to separate the cations from the anions. So even if we know this mean activity coefficient for this electrolyte solution, we do not know gamma plus or gamma minus. We just know over here the mean activity coefficient. So this is equal to, again, this is the definition of the mean activity coefficient. It's the gamma of the cation to the power of the coefficient, gamma of the anion to the power of its coefficient, and then to the power of 1 over nu. Nu is nu plus and nu minus together. And we have this. So again, we know this mean activity coefficient, but we do not know this gamma or this gamma. The mean activity coefficient of this aluminum sulfate solution is much lower than 1 because of the very strong attraction between the solvated aluminum 3 plus and the solvated sulfate 2 minus. And also, of course, there's attraction between the anions and cations and the surrounding water molecules. So all those attractions help stabilize those ions in water and make them less active, and therefore lower activity coefficient than 1. The mean molality of the ions is computed this way. This is just the definition over here. This is the mean molality. We have the molality of the cation squared and the molality of sulfate to the power 3, and overall we take 1/5 over here, and then it's going to be 0.0255 molo. Now we compute finally the mean activity of these two ions. The mean activity is simply the mean molality over m naught. This is just to get rid of the unit, multiplied by the mean activity coefficient. So the mean molality, we have this here, divided by m naught. It's going to be a number, 0.0255 right here. We have the mean activity coefficient, 0.0655 from actually the calculation of this gamma. Given the ionic strength, so we can calculate gamma, plug it in. We have the activity for these two ions, 0.00167. And in the end, the mean chemical potential of 0.01 molo aluminum sulfate solution is this. This mu is the non-standard mu. This mu is the standard mu. What's the difference? The difference is RT times the natural logarithm of the mean activity, which was computed to be 0.00167. Plug it in here.